In the name of God, the compassionate, the merciful, engineering plasticity, chapter 3, yield criteria, part 11. Now we have in this presentation some more considerations for the yield criteria. And as shown in the figure, we have shown this figure before. This is for the Mises and Tresca yield criteria in three-dimensional space. As you can see, this is the deviatoric stress, this is the component of hydrostatic stress, and this is the total stress, OP. Okay, so if P comes out of this circle, yielding occurs. According to Tresca, yielding has occurred in here. And this is the pi plane. Now, we have obtained these values before. OO prime is equal to I1 over root 3. That component, which is the hydrostatic stress. And O prime P also is equal to root 2 over 3 sigma y. Sigma y is the yield strength. And J2 also is sigma y over root 3. Okay, because this is this sigma y is the yield strength, root 3 is a number, so this is a constant. So J2 is equal to constant is the Mises criteria. Now let us do a different thing. Let us plot J2 against I1. Okay, as we know, J2 is constant and I1 is this. Okay, sigma 1 plus sigma 2 plus sigma 3. And therefore, as we can see, because J2 is a constant, it does not change with the stresses. In other words, we say that our yield criteria, which is the Mises criteria, is insensitive to stress variations. In other words, it is not stress sensitive. It gives very good results for many materials, since many engineering materials are not stress sensitives. But some materials are stress sensitives. And we want to know what we could do about them. Now, this is behavior of a stress-sensitive material. As you can see, as the stresses, I1 is a function of stresses, sigma 1, sigma 2, sigma 3, increases, or J2 also changes as well. So it means that this J2 in here, in this case, is stress sensitive. The more the stress, the more reaction is shown in the yield criteria. Okay, so that's how we show the stress sensitive materials. Of course, you are familiar with this line. I have shown this line before for the Coulomb-Moore or modified Moore criteria for the materials which have different values for yield strengths in tension or compression and compression. Now let us go to three-dimensional space and see how it is shown. This one. Now this is the sigma 1 equal to sigma 2 equal to sigma 3 is the hydrostatic line. Okay, it makes equal angles to sigma 1, sigma 2, sigma 3, and it's hydrostatic pressure line. Okay, around which we usually make our yield criteria or yield surface, or yield surface is axis of revolution for the yield surface. Now, this is how a stress-sensitive material yield criteria is shown in three-dimensional space. As you can see, it varies from this Mises criteria to 0 here. Of course, here is not 0, but it's equal to the sigma 1, sigma 2, sigma 3, which does not have any effect on the yield criteria, as we have said before. What is 0 here, in fact, is the deviatoric stress. That is the deviatoric stress. As we come down, as you can see, deviatoric becomes smaller and smaller, it becomes 0 here. Now we call this cone, we call it Drucker-Prager yield criteria, and it is shown by this. Okay, root J2 is equal to C3 plus C4 dot I1. C3 and C4 are constants, and similarly for Mises criteria, we could have equivalent stress-sensitive yield criteria like this. Okay, so the modified Tresca yield criteria, we call it, and this is also sigma 1 minus sigma 2 is equal to, or sigma 1 minus sigma 3, depending on which one is the minimum, which one is the maximum. C1 plus C2 dot sigma m. Sigma m, of course, is this line. This is the hydrostatic line. Now, sigma 1 is equal to sigma 1 plus sigma 2 plus sigma 3 divided by 3, mean stress. So these are the two newly developed yield criteria, and they are for sensitive materials. And the constants are like this. C3 for the Drucker-Prager yield criteria, C3 is equal to 6 times S cos phi divided by root 3 times 3 minus sine phi. What are these S and phi? S is called the cohesion strength, and phi is the friction angle. We will talk about these two in a few minutes further in the slides. Okay, also C4 is 2 sine phi divided by the same denominator. So this cohesion strength, as the name implies, could be used either for geomaterials or for powder metallurgy, and phi is the friction angle, which I'm going to talk about in a few minutes. Okay, then let's see the geomaterials, because we have in this class some students for civil engineering, so I am also going to talk about this for their sake. Stress sensitive geomaterials like these rocks. Okay, for instance, here we can see some stones, and in between some cementation, also here as well some cementation. So the cohesion strength is the strength of this cementation, or something like a glue. Okay, putting all these stones together and keeping them integrated. Okay, so the more strong this cementation, the more is the value for S. Okay, the cohesion strength. Now we have here shown a schematic figure trying to explain what we mean by this cohesion strengths and these geomaterials. Geomaterials usually are like this. Also, powder metallurgy, the parts that are made from powder metallurgy are like this. We have granular structure like this. Okay, this could be a small stones, or this could be the grains in the powder metallurgy. Okay, so let us call them grains. Okay, these are the grains, and as you can see, this yellowish color is that glue that keeps these grains all together. And here we have shown that we have two kind of normal stresses, one in this direction and the other one in this direction. So that's sigma 1 and sigma 2, and this is cemented or glued together. Okay, so in here we have uncemented grains. Okay, these grains are uncemented, and you can see that there is no glue or cement between them, so they have no cohesion, but they have been stressed as before, sigma 1 and sigma 2. So these stresses keep them together. Okay, keep them together. And the question is that whether these grains move relative to each other. For instance, sigma 1, sigma 2, keep them together, but if sigma 1 is greater than sigma 2, and if we increase it enough, this grain may move relative to this grain, or the other way around. So we have shown here a block of material to compare the situation, this one with this one. We have made this simple demonstration to show what happens when these grains move relative to each other. If we consider a block of material like this, then we have a normal stress like this, normal force which causes the normal stress, and we have a force acting here which we call it shear stress, because the force divided by the area, shear stress. Okay, so if we consider this block of material, and if we want to move it, it has to move on this surface. This surface has a friction, and so it has to overcome the friction. Now, here we have shown sigma n equal to Fn divided by A. Fn is the force acting on this area, therefore force divided by area is the stress sigma n, and similarly tau is equal to Ft over A. Okay, because we said this is a cube, all the surfaces on this cube are the same area, so that's why we have written A here and A there. Now, considering the normal stress that is acting here, we want to know what amount of shear stress, okay, should be applied to the block in order to move it. So if we have a certain stress acting here, how much force should act here, or a stress should act here to move it, since we have this friction between the block and the surface in here? That's the question. Now, obviously here, as we increase sigma n, tau increases. So we have a relationship between tau and sigma n. And this also depends on the friction in here, friction factor between, or coefficient of friction between the block and the surface. I should mention here that the slope of this curve depends on the friction on this surface. Okay, so if the slope is very steep, the line is like that, then it means that for smaller values of sigma n we need large values of tau. But if the slope is shallow, like this, then it means that for large values of sigma n we need smaller values of tau. So the more the friction, the slope of this line will be steeper, and the lesser the friction, the slope of this line is smaller. Therefore, if we consider this granular medium, then the grains, these are the grains, move relative to each other, as I said. If, for instance, you keep sigma 1 constant and increase sigma 2, then these move relative to each other, or vice versa. Okay, so we call these stress sensitive materials, and geomaterials are stress sensitive. And if we add a cementation here also, the same thing holds, but with different equations. Now, let us see, examine this a bit further. We have this sigma n normal stresses acting on these grains, and what is the sigma n? Due to sigma 1 and sigma 2, we have a sigma n on all of these contacts here. We have a contact that is normal to the surface, which we call it sigma n, normal stress. And we have a shear stress like that, okay? Because if there is a force acting on this contact surface due to sigma 1 and sigma 2, then we could resolve that force in two directions, tangent and normal. So that's what we have done, sigma n and tau. The force divided by the contact area is sigma n, and the shear force divided by contact area is tau. So as you can see here, this is very similar to the block that I just showed you, and we could use this simulation to derive our formula. Now here again we have tau and sigma n, like the case with the block. The same thing is true here. As we increase sigma n, it becomes more difficult to move the grains relative to each other, and therefore tau increases. This is the same thing as the Coulomb-Moore criteria, which I explained to you before, but I just wanted it to apply it to a real case to see how it works. Okay, so this is the same as Coulomb-Moore circle. This sigma 1 and sigma 3 are the principal stresses, and we say that if we go above this line, failure occurs. If we stay below this line, we are okay and it does not fail. So that's how the yield criteria works. And of course here you see that this is where we have the maximum shear stress, but that's not the point of failure. Point of failure is here, where from C, the center of the circle, we drop a perpendicular to this line, and that is the shear stress at which it fails. Okay, because if you want a higher stress, you have to draw a circle, for instance, here. Okay, then you have higher shear stresses. So that's how it works, and we can see that this coefficient of friction is the angle of this line, and it can be shown like this: tangent phi is equal to mu. Okay, mu is the coefficient of friction, and this line shows the relationship between tau and sigma n, which is related to tangent phi, which is coefficient of friction. As I mentioned, in the case of the block moving on a surface, the friction between the surface and the block determines this mu. So here the friction between these two grains, the surface of these two grains, determines mu, and mu is equal to tangent phi. That's why we call this phi the angle of friction. Okay, angle of friction. It can be increased or decreased. So the mu increases or decreases the friction, and tau increases or decreases relative to the normal stress. in here we can find out the relationship between sigma 1 and sigma 3. As you can see, sigma 1 could be written as OC plus the radius of the circle, and sigma 3 could be written as OC minus the radius of the circle, which is R. And also this radius in this triangle could be written in terms of OC, in fact OC sine this angle, which is phi, so OC sine phi minus OC sine phi. So here we get OC cancels out and we get 1 plus sine phi, 1 minus sine phi. And therefore sigma 1 could be written in terms of sigma 3 times this ratio. We call this ratio Q. Therefore sigma 1 is Q times sigma 3. Typical values for Q, which is equal to 1 plus sine phi divided by 1 minus sine phi, is 3. If phi is equal to 30 degrees, Q becomes 3. This is a typical value in the geomaterials. So for granular materials we use this typical value. Okay. Now if you consider volume like this volume includes these grains or granular particles. These granular particles are confined by these stresses, sigma 1 from here, sigma 3 from here. I have just shown a part of these granular particles. All over the place these granular particles exist, but I have just shown part of it for clarity, because I just want to draw something here, so I don't want to be too much confusion here. So these particles are all over the place in this volume. Now we have confined these particles by sigma 1 and sigma 3, and then obviously these particles relative to each other have shear stresses and normal stresses as well. And here obviously we could write the shear stress in terms of normal stress and friction angle. Okay, so if we consider this volume, then this is, supposing this is a rock. Okay, this is a rock which consists of these granular particles, or this could be a mechanical part which has been manufactured using the powder metallurgy. So these are the powder particles. If it is confined by these stress values, principal stresses sigma 1 and sigma 3, then as usual in the Mohr circle, now in the Mohr Coulomb circle, we know that whatever angles we have here is divided by 2 in here. For instance, the plane of sigma 1 is here and sigma 3 is here. So sigma 1 relative to sigma 3 is 180 degrees. But in the physical actual problem, we have these planes, that is sigma 1 plane, that's sigma 3 plane, which is 90 degrees. So 180 degree, 90 degree. So all the angles in here should be divided by 2 in the physical problem. What I have shown here is a plane. This line, in fact, represents a plane. Similar to the reasoning that I have just mentioned, this plane makes an angle 90 plus phi over 2 with the plane of sigma 1. Why is that? Because phi, in fact, is that angle. This is perpendicular to that. This is perpendicular to this. Therefore, this angle is phi. This angle is phi, and as can be seen, this is phi and this is 90. Okay, so that angle is 90 plus phi, and in the Moore circle space the angles are twice the angle in the physical real space. So that's 90 plus phi divided by 2, and that's where the shear stress happens. Okay, the shear stress in fact causes failure on this plane, and as we mentioned before, if phi is 30, then that would be 90 plus 30, 120 divided by 2, 60 degrees will be the plane inclination of the plane on which the failure occurs. The shear stress becomes maximum, reaches the critical value, and a slip occurs and it fails. Okay, so that's the mechanism of using this stress sensitive geometry, using the criteria, yield criteria for this kind of materials. In here I have shown this again, but I have written here uncemented. Okay, so it means that these particles or granular particles are all attached to each other but not glued to each other. Okay, so there is no cement or any glue or anything. Okay, just the particles alone. That would be the case for the case that they are uncemented. But when they are cemented, okay, supposing we pour some cement or glue inside these, and they are all attached to each other, and there is a strength, increase the strength between them. Okay then, so the new line will be here, and this S0, as mentioned before, is the cohesion strength between these particles, while in here we didn't have any cohesion strength. It was 0 because there was no cement or glue or anything, but here we have this. So depending on that, on the material that we have put between these particles, the cement, how much adhesion that has, how much cohesion that implies, then this S0 will be less or more. Supposing for a cementation, that is cemented material in here, we have S0 in here, and the line will have the same angle phi, and that's the angle phi, and we could write it in other words like this, 1 and mu. So the tangent phi is mu, in fact, as explained before. That's the coefficient of friction, and we can write tau, we wrote it here as mu dot sigma n. So we add this S0 or cohesion strength here, and so we have the shear stress equal to S0 plus mu dot sigma n. That is obviously more than that, and so for cementation we need more stress to make it shear and let fracture happen. Now in here we have, you see in this picture we have the axes are tau and sigma n, okay, shear stress and normal stress, and we have this sigma 1, sigma 3 in here, but in this figure we have used the axes sigma 1 and sigma 3, which are these principal stresses. And for this one, which is uncemented, we have this line like before, but here we have sigma 1 q dot sigma 3, okay, because the gradient is q, that's tangent phi is equal to q, okay. And for cemented particles or rock, we have this line, okay, like before, except that here we don't have tau and n, we have sigma 1 and sigma 3. So sigma 1 is USC, is that interception, plus q dot sigma 3. USC is in fact the unconfined. Unconfined means that unconfined S, because before it was S0, it's now unconfined strength. Unconfined strength means that as you can see, sigma 3 has become 0, so it's not confined, no stress on this direction, so only stress in this direction, it can move in that direction. So S sigma 3 0 is USC, unconfined strength. And as you can see, sigma 1 is USC plus q dot sigma 3, compare these two, and we can find this relation between USC and q and S0. In fact, between this figure, okay, S0, that's tau and sigma n, and this figure, which is sigma 1, sigma 3, and that's USC, and that's q, okay, because we have q is equal to this, okay. So you should be able to find this relationship between these two as well. I think this is all I would like to talk about these Coulomb-Moore and stress-sensitive geomaterials. Obviously, we can talk a lot about this, but it is out of the scope of the engineering plasticity. Civil engineers will study more in other subjects in their course. Right. Now we are going to discuss the anisotropic yield criteria in the next section.